Welcome to Calculus BC video for skill number 253. I can find the average value of a function on a given interval. And featured to the right is a picture, a classic picture of a old big-wheeled bicycle. And the trivia question for the day or for the video is, why were the wheels so big on old bicycles? Alright, so let's assume that what we have is a function, and our function looks kind of like this. And what we want to do is we want to find the average value of the function over an interval. We'll go from we'll say time 0 to time 10. So over our interval of time 0 to 10, what is the average height of this function? You know, maybe a bad guessing person might say, oh, the average value is right about here. Another person might guess up here. But obviously the value is, well, maybe not obviously, but probably the value is somewhere between these two lines. Maybe we'll guess somewhere around here is the average value. The way we go about finding the average value is actually what we can think of as we're looking for what height would make a rectangle of equal area to the area under the curve. So the area under our curve is, you know, we can find with an integral. And the area under a rectangle we could actually find geometrically. We see that the base of it is 10 units long and the height is whatever we find it to be. So the area under the curve we know as being the integral from a to b of our function. So if we want to find some sort of rectangle with that same area, I guess we would say we'd have some height. We'll call that our height times our width, b minus a. And we get that function. That height would be our average value for the function. So we can actually move the b minus a over to the other side and get the equation. So let's take a look at that on our notes page. If we have a function that's continuous on the closed interval, like we discussed, the average value of the function, which some people call y bar, is equal to, here's the 1 over the width of the rectangle times the function doing the integral of the function over that. It's a pretty straightforward formula, especially if you understand how it was derived. So it's very closely related to the mean value theorem over an integral. Sorry, I mean integral. The mean value theorem is basically this equation. Not basically, it is this equation, which basically says that there is a value, which we'll call u. There is a value u so that the function at that value times the width of the interval is equal to the integral. In truth, you could really think of this as synonymous. They're just two different ways of looking at the same concept. So let's use that. Find the average value of the function 3x minus 8 on the closed interval 0 to 2. Well, our average value equation says y bar is equal to 1 over 2 minus 0 of the integral of 0 to 2 of 3x minus 8 dx. So if we go about simplifying that, the front is 1/2. Our integral will become 3x squared over 2, let's do it in red, 3x squared over 2 minus 8x, and that's evaluated from 2 to 0. And then we plug in those numbers and see what we get. This is equal to 1/2 of 6 minus 16 minus 0. So I'm not even going to write it. 6 minus 16 is 10, or negative 10 times 1/2. So we have an average function value of negative 5. If we were to think about that visually, I'll just scroll down here. 3x minus 8, and that's something like down here at negative 8. We have a slope of 3. So between 0 and 2, our average function value is right there at 5, negative 5. So the blue trapezoid carries the same area as the red rectangle.
Wow.
All right, so 2 application problems with this. A rod that is 3 meters long is heated to 25x degrees Celsius, where x is the distance from one end. So we have this rod, and we can say at 0 meters, we are 25 times 0 degrees, so it's 0 degrees here. At 1 meter, we are 25 times 1 degrees. At 2 meters, we are 50 degrees, and at the full 3 meters, we're at 75 degrees. So it's very hot towards the right side of the stick or rod, and it gets colder as we get closer to the end of the stick. So what we're trying to do is find the average temperature of the rod. Well, our lower bound is 0, and our upper bound is 3. And our function for temperature is 25x. And then for average value, we're going to do 1 over b minus a. And this will give us our average value for the temperature. That's 1/3 times 25x squared over 2 evaluated from 0 to 3. Giving us a final answer of 37.5 degrees, which you'll notice is probably the temperature right at the midpoint of that rod. And it kind of makes sense because it's a linear equation. If our temperature was heated in a nonlinear fashion, then it would be weighted to the left or right of that point. All right, a more sensical one is average daily rainfall. So the rainfall per day after the beginning of the year is modeled by the function r of x equals da 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 da, measured in centimeters. Find the average daily rainfall for the first 180 days. So that means our interval is from 0 to 180, and we have our function r of x. So if we want to find the average daily rainfall, we are looking at 1 over 180 minus 0 times our r of x, which I'm just going to write r of x dx, and it's evaluated from 0 to 180. And this looks like the perfect sort of problem to do on a calculator because it's got some nasty numbers and probably could evaluate it much quicker on a calculator. So remember, what we're going to do is we're going to do 1 divided by 180, put that in parentheses, times our function integral. And we can type out all of r of x. Maybe we stored r of x under y1. I like to look at it graphically, so I stored it under y1. We're integrating it with respect to x from 0 to 180. And if we typed it all correctly, we should arrive at an answer of 0.573 centimeters. The somewhat fascinating side fact or side thing to note is I graphed this function just to see what it looks like over the interval of 0 to 180, and it does something kind of like that, which means there's little rainfall at day 0 and a high amount of rainfall at day 180. And that being said, I would say that this is probably a problem written for something in the southern hemisphere where the middle of the year is getting the most precipitation and the start of the year gets the least, so it's summertime in January. That's just me geeking out. All right, thanks for watching the video. Hopefully now you can find the average value of a function, which is basically if you had some sort of curve and you had your area under the curve, there is some point, let's say from here to here, there's some point along here which would capture the average value of the function. And you can think of it geometrically as being if you collapsed all of the area into a rectangle. The height of that rectangle would be the height of the average value of your function on that interval. Okay, and the answer to the trivia question is, why were the wheels so big on classic bicycles? So there's actually a couple of reasons. First, for speed. Bicycles did not have gears. You can see this, there's no gear in this bicycle. So having a larger wheel when you're pedaling allows you to cover more distance. The other reason is because back in the times of these bicycles, the roads were not as smooth, and so when you have a bumpy road, having a large wheel decreases the effects of that bump and makes it easier to go over because the angle of climb has been greatly reduced, if you can picture that. All right, thanks for watching.